Hey guys, how's it going? Welcome to your 9th tutorial. And in this tutorial, we're going to be going over a pretty cool computer science topic. It's really theoretical, but it's very cool. And actually, first let me talk about test 2. So a lot of you guys made some comments on Piazza about some of the test cases for test 2, and a lot of them did turn out to be I don't know what the right word is, but definitely not the most fair or the most clear, something along those lines. So Professor Moore has taken a look at them, and he's gonna make some adjustments. And it's looking really good actually for the grades, because the grades might go up quite a bit. There's like a maximum increase of like roughly 8 points. And 8 points, I forget what your test was out of, but I think it was somewhere around like 24. So 8 points is like a third of the test. So someone who got absolutely pummeled by the incorrect test cases and should have gotten everything right otherwise might see an increase of like around 30%, which is like crazy. Like that's an amazing increase. But yeah, we'll see, and hopefully anyone who might have not done well as of right now will see a better grade in the future. Yeah, they were not the nicest, but anyways, binary search trees. This is a topic that we're going to be going over today, and what they are is they're a data structure. So they're a structure in which we store data in a certain format, and you can take a look here. I have a little description up here, which you can read if you want. It basically says that every node in the tree can have up to 2 child nodes. It can have a left and a right child node, and they have to contain orderable information. So, like for example, integers are orderable. You can sort them, and basically the rule in organizing these binary search trees is that every node that's in the left subtree of a given node has to have values that are lower than the value in the root node. So if you look at this node up here, which is 8, everything in this whole tree that I'm circling right here, since it's part of the left subtree, all of these nodes are less than 8. And all of the nodes in the right subtree are greater than 8. And the same rule applies to every single node here. So if you look at this node 3, everything in the subtree, for example 1, is lower than 3, and everything over here is greater than 3. And so this pattern goes on. And the reason why this is used is because it's really efficient to extract data. If you have data that can be stored in an ordered way, and you put them in a binary tree, searching through that data can be cut down dramatically. Because let's say you were looking for the node which contained 14, for example, and you start right here at the root, which is 8. Then you instantly know that you don't have to search through any of this left subtree because 14 is greater than 8. So there's no point looking over here because these would all be less than 8, which can save you a tremendous amount of time. And we'll talk more about the actual numerical performance and something called big O notation just in a little bit. But yeah, this is a very efficient data structure when used appropriately. So we're going to be basically creating a binary search tree class in Python with a bunch of different class methods for it. So you can see them right here. We're going to have a maximum depth function, which is pretty self-explanatory. It just tells you the maximum depth of any given BST. BST is binary search tree, of course. So if you look at this example tree that I pulled from the wiki page right here, it's just the first one. By the way, if you guys want to read more about it, like this wiki page is a great resource. But yeah, in this example, the maximum depth is 3, because the maximum depth is right here defined as the number of nodes in the longest chain of the tree. So 1, 2, 3. You might consider it as 4, but the way they're computed doesn't include the root. So this is considered a tree. So 1, 2, 3, 1, 2, 3, 1, 2, 3. And if you look here at the if you look here at the depth in the caption of the Wikipedia picture, you see that the depth is in fact 3. So that's how that works. So we're going to write a function that gives us the max depth for a given BST. We're going to write another function called search. And basically, you give it a number, and it's going to return true or false based on whether that number can be found in the BST or not. So that's pretty self-explanatory. If we searched for 7 here, we would return true because it's right here. If we searched for 9, we would get false because there's no 9 at all anywhere in this binary search tree. We're also going to write an insertion method, which basically adds a given integer into the binary search tree while preserving the rules of the binary search tree. So we can't just stick it anywhere. We have to stick it in a spot where it preserves the rule where everything on the right has to be greater and everything on the left has to be less than for any given node in this tree. And finally, of course, we need to write our constructor. That's probably the most important one. The constructor is going to be what creates any given instance of a binary search tree. So every time we create a binary search tree, our constructor gets called. And you can see here it takes a list or tuple of integers and constructs a well-formed BST as a result. And we raise value error if invalid input is provided. So that's not too bad. We can probably get going. So first we need to make the class. So let's call it BST. And let's make our constructor. If any of you guys have any questions at all, anytime during this tutorial, just feel free to ask, and I'll stop and try and explain. If anyone has any questions, by the way, already about how a binary search tree is laid out, or the format, or any of these rules, or any of these methods, just feel free to ask, and I'll stop and try and answer. So we're writing our constructor, and what I like to do whenever I make a constructor, or any given function for a class, is always take care of the exceptions first. So if we know that we're supposed to throw some sort of exception on some sort of input, it would make a lot more sense to take care of that first and then do what we need to do later on. So let's get that out of the way. We know that it has to be a list or tuple. This input L has to be a list or tuple. So if the type of L is not a list or tuple, in other words, if the type of L cannot be found in this little tuple right here, which contains the type list and the type tuple, then we're going to raise a value error. Simple enough. And there's also one more check we have to do. We have to make sure that every element inside this list is an integer. So we can run a for loop to loop through the whole list and make sure that everything inside of it, every element is an integer. So say for element in L, if type of element is not equal to int, then we're also going to raise a value error. So hopefully that makes sense too. And that takes care of the error. These are the two conditions in which we would raise a value error according to these instructions, right? Now we can actually do the real work of the constructor. The way we're going to do it is we're basically going to create the root node and then insert every other node afterwards. So what do I mean by that? I mean, if we were given 8 as the first value of the list that we provide as input, we would stick in 8 as the root of the node, and then every integer that follows 8 in that list, we would insert onto the tree using our insert function. We're going to write our insert function so that it follows the rules, and here, so long as the structure of the tree is not violated and the orderness property is preserved. So our insert function is going to take care of following the rules. So in our constructor, we can just call the insert function and basically assume that it's going to keep everything safe for us. So we can, we can do that. What you also need to know is that every node has a left and a right node. Even if it doesn't actually have a left or right node, we still need to be able to refer to a BST as having a left or right. And if it doesn't have one, then we'll just call it like a none or something, or null. So we'll assign left to none here. I'm going to use none instead of the actual none because it's easier to print that way. So let's actually call it null instead, because that makes more sense as like a null pointer, if any of you guys know what that is. We'll do the same thing for the right because we start off with no children. And then every node and every BST also has a value. So the value of the root, which is what we're starting with, is going to be the first element of our input list. And then what we're going to do is, with the rest of the list, we're going to insert one by one every element into our BST. So we can say for n in L, and then we'll do a little slice here that basically excludes the first element that we already grabbed here. So we use the first element, we want to take care of the rest. So for n in L from 1 onwards, we will insert n. Very simple. We haven't actually written this insert function yet, so we should probably do that. That actually takes care of the constructor, sorry. So let's write self. It takes in some node. We can call that node v. And here is the tricky part. We have to figure out which subtree to place every node that we want to place, depending on whether the value that we're trying to insert is less than or greater than the value of the node that we're inserting to, right? Because every node can be treated as a BST. That's the way this whole thing works, is that this root node is basically a BST of the whole tree, but at the same time, this 3 over here can be treated as a BST of its own, which has its children, right? So 3, this BST, will contain 1 on its left, and then 6, 4, 7 on its right, and that can be considered a BST object of itself. And so we need to check where we should insert our node. So this is how we're going to do it. We're going to say if the number that we're trying to insert into the tree is less than or equal to the actual value of the root of the BST, then we know that we need to put it on the left subtree somewhere, right? Let me actually make a comment here. I'm going to make a design decision. And since we're allowed to have duplicate elements, that's why I have this less than or equal to, because there is a possibility that something you're trying to insert already exists on the BST. So what we're going to say is that if it already exists, then duplicate elements, will put them on the left subtree instead of the right. That decision is pretty arbitrary. It doesn't really matter. But yeah, we'll just say we'll put nodes with equal values, with equal values on the left subtree. So that's something to note. And then we have to actually check something else. We have to make sure if the left is already a null, which means if the root that we're looking at doesn't have a left, then we can actually just stick it right there as its own BST. And I'll show you what I mean by that. If self.left is equal to null, then self.left will become a BST just containing v. So BST here, we're calling the constructor again because we're making a new BST object, and we're passing in that node. The reason being, so see here, I'm saying if self.left is equal to null, then self.left becomes a BST of just that one node. And I'll show you what I mean. If we try to, actually that's a bad idea. shoot. Let's say there was a number that was less than 1. Let's say you can have negative values. So let's say I wanted to insert -2, right? -2 is less than 1. So we want to put it on the left subtree, right? But the left subtree doesn't exist. So if this is self, if this node right here is self, then self.left is equal to null right now. So what we can do is we can assign self.left as a new BST of just that one node. And that links back to what I told you guys earlier, that every single node can be expressed as its own BST. So if you have a BST that's just one node, then we can stick that BST as the left child of this one node. And so -2 can go on right here. Let me actually, I'll snipping tool this. And I'll bring it into Paint, just in case we want to take a look later on. Okay, so that's the reasoning behind this. And then you might ask, well, what if the left is not null? What if it already exists, right? For example, if we try to insert onto 3, if we try to insert 2, but there's already a 1 here, right? What do? Well, the answer is here. We'll say else, right? If self.left is not equal to null, which means it exists, then we'll just insert, which you might notice is we'll insert it into the left subtree, which is recursive now, because we're calling insert inside the insert definition. And this brings you to this base case. This is kind of like a base case right here. That takes care of the 2 cases for when we're trying to insert onto the left, right? If phi is less than or equal to self.value. So we basically need to mirror this for the right? If phi is greater than self.value, notice that we're not doing greater or equal to, because equal to, we're going to put it in the left subtree. So if v is greater than self.value, and this is going to be right, because we're basically saying the same thing, but with right. So if the right is null, then the right child will become a BST of just that node that we're trying to insert. And if it's not null, then we'll just insert that node. That should be it for insert. I'm pretty sure. If any of this stuff isn't making sense to you guys, it will make a lot more sense when I actually run the functions and I demonstrate what's happening with the BST. But like, for example, I can try and explain this recursive call, if any of you guys are not understanding that. So there's a recursive call here, and there's a recursive call here. We only pick one of them though, because it's under an if statement. So we insert either into the left subtree or into the right subtree, depending on whether v is less than the root's value or whether it's greater than the root's value. So suppose we were trying to insert the number 2 into this BST, the BST with the root of 3. Well, we'd ask ourselves, right? We say, is v less than or equal to self.value, or is it greater than self.value? Well, v is equal to 2 here, and self.value is 3, because the root node is 3. So 2 is less than or equal to 3, so we're inside this if block, right? So we're inserting 2 here, and then we ask ourselves, is self.left equal to null, or is it not? Well, self.left of 3 is this 1, so it's not equal to null, because it's equal to the BST of 1, right? So we would insert into the left subtree that v node. So now we're inserting into 1, right? So now this recursive call comes back, and now we're passing 2, but we're inserting it into the 1. So then we ask ourselves, is v less than or equal to self.value, or is it greater than? And the answer now is it's greater than, because self.value is equal to 1 now, and v is still 2. And then is self.right equal to null? And the answer is yes, because there is no right child for the 1. And so we assign it to the BST of just that one node. So hopefully that makes more sense now. Recursion can be a bit difficult to understand sometimes, but I hope that explanation kind of showed you guys how the recursive call will terminate. And so after insert, we're basically kind of like going the opposite direction, where we wrote the constructor, we wrote insert. Now we can write search, which returns true or false, depending on if we can find the node v in the BST. This is actually going to work very, very similarly to our insert in the way where it kind of separates the left and the right subtrees. So let's come up with a base case first, right? If the node that we're looking at has the value of v, then we can return true right away. So if self.value is equal to v, then return true. And the reason being is, let's say we start here at 8, right? If we're looking for 8 and we start here, then self.value is equal to 8. So we've already found the node. We can just return true right away. And you can probably see that what we're going to do with this is we're going to make it recursive. That way we can call search on the left and the right. And hopefully that's going to start making sense to you guys. If we call it on the left, and let's say we're looking for 6, okay? Is 8 equal to 6? No, so we can't return true yet. But we can search the left and the right. So we'll recursively search the left and the right. So we'll search the left first, right? We'll say, is 3 equal to 6? No, it's not. We can't return true yet. So we can search the left and the right. Is the left equal to 6? No. Is the left equal to 6 of 1? Well, it's null. It doesn't even exist. Is the right equal to 6? It doesn't even exist either. Is the right of 3 equal to 6? Yes. And then we can return true. And notice that that's how the recursion kind of goes down and then climbs back up. Is we keep going and then we get down here, and the base case is going to be if it's if there are null children, right? If the children don't exist. So let's try and write that. So obviously, if the value is equal to v, then we can return true right away. But otherwise, else, we have to check to see if the children are null or not. So let's start off with the left subtree first. If the left subtree is equal to null, then let's make a variable called left found, and we'll give it a value of false. And if it's not null, so if the left subtree actually has a subtree in it, then we can recursively call our search function on that left subtree. So we can say self.left.search v. And that takes care of the left. So we can just copy this and do the same thing for the right. Yeah. And the cool thing here is that we might find our node in the left or the right subtree. It's going to be in one of those two. So we actually have to return true if it's found in the left or if it's found in the right. If one of those is true, then we've successfully found the node in our BST. So what we can do here is we can return left found or right found. And hopefully that makes sense. I can try and explain that as well. It's basically the same thing that I just showed where we were trying to find 6. We end up traversing, and as soon as you hit a null, you set it equal to false. But if you find it on a given recursive call, then it comes up true and you climb back up the recursion trace. So you search here, boom, boom, null child links on both of these recursive calls. So left found is equal to false, and right found is equal to false. So this is false. So the left of 3 is false. The right of 3 is true because we found 6 right here. So the search call of 3 is going to be false or true because we found it on the right, right? So false or true is true. So 3 is going to be true. And then 8 is equal to left found or right found. So it's 3 or 10, right? And we just said that 3, it came back as true. So true or false, whatever this ends up being, true or anything, is going to be true. And so our recursive call that started from 8 up here at the root will come out to be true. That's the idea. And obviously, if you can't find it, then you would have never gotten true because this condition would have never hit. And this is the only time where we ever return true in the search function. So that takes care of the search function, I think. We could basically write our last function. Do we need to set left found equal to true if it is on the left? Did I do that or did I not do that? Yeah, so if it's found on the left, then this recursive call will come back as true. Because it's recursive, right? So search here, search there. This else statement, it's going to do the same thing. And if we end up finding it, then it's going to come back true. And it's going to climb all the way back up. And it's going to come back true. We don't actually have to explicitly set left found equal to true. Because like it would be set to true right here. Like if you call this recursive call, it will run this function. So self.left.search, if self.left ends up being, if self.left.value is equal to v, then we return true. And so self.left.search v will be true. Oh, I see what you mean. Yes. We actually have to, my bad. Sorry, Marvin. We have to assign them. I forgot to assign them. So left found equals there. I think that's right. And the same thing. Yep, sorry. Right found equals self.right.search. So those we'll call recursively. And if this recursive call comes back as true, then we'll store it in left found. Thank you for catching that. I think that should be it for search, unless I screwed something else up, but it looks to be good. We can write our maximum depth function, which is the last thing we got to do. I don't think it takes any arguments. Yeah, it doesn't take any arguments. And it's not too bad to write either. So I'm sure you guys can probably guess that the way we're going to do this as well is recursive. Basically, the pattern here with these BSTs is that everything can be done very easily recursively. And it's actually very hard to do it without recursion. So let's say we were trying to find the max depth of this tree, starting at the root 8. How would we do that? We can try and think of some strategies, but basically, we would take the maximum of the max depth of the left subtree and the max depth of the right subtree. So if we're looking for the maximum depth of this whole BST, why don't we find the max depth of this one, and then the max depth of this one, and then take whichever one's higher, right? And that's exactly what we're going to do. But there's one catch, is that the max depth of this one is, let's see, it's 1, 2, right? But if we just took, and let's see here, the max depth of this one is 1, 2, right? 10 to 14 to 13. is 2. The max of 2 and 2 is 2. So does that mean the max depth of 8 is 2? The answer is no, it's 3. And that's because you have to add 1 every time you go down the trace, right? Because when you take the max depth of this tree starting here at 3, then you're ignoring the root node 8. So you have to add 1 to make up for the fact that you have the root node 8. And then you can actually count 1, 2, 3. And that's the max depth. So we can write our function here. We can take care of the base cases first. So if it's null, then let's make a variable called left max depth, and we'll set left max depth equal to 0. Because if we were trying to find the max depth of this BST starting here at 4, well, it would be 0 because there's no depth to it. There's no children, so it has no depth. And similarly, we can do the same thing. Actually, let's not do that. Let's take care of the whole left first. So if the left, like we can take care of the whole left first in the same way that we did for insert and search, right? So if self.left is null, do something. If it's not null, aka else, we can do something else, which is our recursive call, as you probably would have guessed. So we're going to set left MD equal to self dot left dot max depth plus 1. So we're going to recursively call it on the left, add 1. We're going to do the same thing that we did over here for our right. Rename these variables. And that's it. Oh, okay, no, we still need to return the max, right? Because we're basically, at the end of this, we're going to have a left MD, which is going to basically tell us the max depth of the left subtree, and a right MD. But we actually have to return the maximum of those two. We can actually use the Python command max, which basically takes in some list or a tuple or a bunch of different numbers, and it just spits out the max. So left MD, right MD. And that's it, I think. Sweet. We have taken care of every single function. Let's also make a string method. I'm sure you guys are familiar with your string method by now. We weren't explicitly asked to make a string method here, but I think it would be useful to make a string method to kind of show you what the tree looks like if we tried to print it. So making a string method for our BST is going to, oh, is it not indented? It's not, thank you. Very, very good catch, I'm slacking. Yeah, this return should be indented. So, yeah, if we were able to print out our BST, it would probably help us a lot to visualize kind of what's going on. And the idea here, what we're going to want to do is, once again, it's going to be recursive. And the idea is that we want to print the value and the whole left subtree and the whole right subtree. Oh, you weren't talking about that one? Which one were you talking about? Oh, no. Wait, should that have been indented or no? That also should have been indented. So double catch. Made 2 mistakes. It's amazing. Yeah, so we want to, I'll make a comment up here. Print the value of our current node, as well as the whole left subtree and the whole right subtree. So we can return string of self.value, which is going to be a number, right? Self.value is always a number, because as you can see up here, we assign self.value to the first element of our list, and we have a list of numbers, plus self.left, and this is where it gets recursive, because self.left is a BST itself. And in order to string a BST, we need to call this magic method function. And we're going to do the same thing for self.right. Maybe it also might be helpful if we add some more text to kind of show us what's going on. We can make some new lines to make it easier, and we want to signify that this is the left subtree, so we can do that. And do the same thing for the right. At the end, we can close it. We can have the same sort of thing going on here. All right, that looks pretty good. We can see how that goes. Let's try running it first and see if we hit any compile errors. We do. Oh, there's a plus here. Okay, it ran. No other errors. So let's try and use this big class that we just made to make a BST. And then we can start using these functions that we've just written to build the BST and to print the BST. So we'll insert a new cell below. And let's say, call our BST X, and we'll say, let's actually make the one that is in our example. 8, 3, 10, 1, 6, 14, 4, 7, 13. 8, 3, 10, 1, 7, 6. What's the rest? Oh, 1, 6, 14, 4, 7, 13. Okay. We run that, and boom, our BST was created just fine, which means that our constructor was good. Let's try making one of these a float, like 4.5 or 6. There we go. Our value error was raised because one of the elements wasn't an int, which is good, so we know that works. We can even try and pass in like something that's not a list or a tuple, like this 8, and we still get a value error. So we'll bring it back here to a valid input. And what you can see is that what happens here is that we actually call insert when we make a BST object. So all of these nodes got inserted. So our insert was just ran. Let's try and check the max depth of this tree to make sure that it's actually the max depth that we think it is. So we can say print x.maxDepth. We get 3, which is good because we had originally shown this tree to be of max depth 3 as well. And we just emulated that same tree as an example here, which is like 1, 2, 3 is the max depth you can get to here. Let's also try and search. So we can print x.search. Let's search for 13. True, which is good because there's the 13 right here. Let's try 10. True, because there's a 10 right here. Let's try 9. We get false because there's no 9 here. That's good, so that's working. It looks hella gross when you print it. Yeah, it is gonna look hella gross when you print it, but we'll still be able to decipher it, hopefully. We'll get to that. Let's also try the, what else should we try? We can try inserting ourselves. But let's print it first, and then we can insert to show you guys what happens when we like the difference after we insert on the way it prints. So to call our string magic method, we can just print the BST. So we can print x. Oh, yeah, that's not the prettiest. It's not the most legible, but it is in fact legible. And let me show you guys how it's legible. So we start off with 8, which is our root, right? And as you can see in our string function here, we stringify the left and we stringify the right. So every subtree is going to be evaluated in that same way. When you break this recursive call down, it's doing the same thing. It's doing left, then right, then left, then right, then left, then right. So what's going to happen is when we call string on this BST, starting at this root 8, we're going to get 3, then 1, then whatever is the left of 1, which doesn't exist, then the right of 1, then the right of 3, then the left here, then the right here, then the right here, left here, right here, and it's going to climb all the way back up. So that's how the recursive calls work, right? Because we're like, every time we visit a new node, we try and visit its left and right in that order. So if you can see here, we have 8, and the left of 8 is 3. And the left of 3 is 1. And the left of 1 is null, which makes sense, because that's what's happening. 8, the left of 8 is 3, the left of 3 is 1, and the left of 1 is null. And then the right of 1 is also null. And then you can see here we close it off, right? We close it off because once you finish printing a whole BST, we end it with these double angle brackets right here. So the 1, this BST right here, finished. We printed its left and its right. So we have the double angle brackets right here. And then we print the right of 3, which is 6, and the left of 6, which is 4, and the left of 4, which is null, the right of 4, which is null, and then we close it because we finished 4 as well. So as you can see here, the same thing reflects. We did left, right of 1, we climbed back up here, we did the right of 3, which was 6, we did the left of 4, or sorry, the left of 6, which is 4, we did the left of 4 and the right of 4, which means we finished 4, and that's why we saw the other angle bracket. And then it's going to climb back up to 6, do 7, visit its left and right, which are both null, and then climb back up here. And then we're going to climb back up here, and then we're going to climb back up here. So what you're going to see is after this right over here, we finish 3 BSTs, right? We finished the 7, but we've also finished the 6, and we've also finished the 3, because we've explored and printed their left and right, which is why you get those 3 closed arrows in a row, because we've finished the string function right here of 3 in a row. And then you look at the right of 8, right? Because we had 8 over here. This whole section was us printing the entire left subtree of 8. Like all of this stuff down here. So now we have to print the right subtree of 8, and then we can close off 8, right? And that's what happens in basically the exact same fashion that we did the left. And yeah, it's not the most pretty, but it does get the job done. And so what we can do here is we can try and insert. So we can do x.insert, and we just pass something in. So let's take a look here. What do we want to insert? Let's try inserting 9. 9 would be a good insert. 9 is greater than 8, so we would insert it into this right subtree. But 9 is less than 10, so we would insert it on the left subtree of our 10 node right here. So it would end up right here, because since the left subtree of 10 doesn't exist yet, it's null, the left subtree becomes the BST with just 9 in it, which is this. It's this right here, right? So if we inserted 9, oops, that's not what I wanted to do. Insert 9 and then print x again after. Okay, I don't like that. Let's make a space between them, right? So this is our subtree initially. This is our subtree after the insert. So you remember right here where we have the first 3 angle brackets is when we finish printing 7, then 6, then 3. So we finish the left subtree entirely, and that's why we have those 3 angle brackets, which means we start over here. So we say that the right of 8 is 10, and boom, here it is. Our 9 is now the left subtree of 9. The 9 is the left child of 10, which would make sense because the 9 would go right here, right? And then you'll see 9 is the left subtree of 10 right here, and the left of 9 is a null. The right of 9 is also a null because 9 will not have any children. And that's the whole idea. That's what a BST is. And those are the main functions that you will see on a BST. Things like insert, search, and depth. Does anybody have any questions at all on BSTs or any of the functions that we've written for them? I'll save the notebook, and this will once again go on Avenue. But yeah, these recursive functions aren't the easiest thing to just instantly grasp. Is there any way we could print it in a format like the one presented in the image? That would be tricky. That would be pretty tricky because of the way our recursion works. I'm sure there is a way to do it, but I don't think it would be easy because with our recursion, we would print a left subtree, like it would trace down the whole left all at once. If you think of a way to print it and actually format it nicely, feel free to share it. That would be probably a nice thing to try and do on your own. If you download the notebook, you can say challenge. Create a function that prints the tree in a similar format to the image. Yeah, I don't think you'd use recursion for that then. I think you would you'd use recursion and then maybe you could add to like a stack of some sorts, or you could queue them up, or you could run through it iteratively. That's also definitely a possibility. Like I'm sure you could just you could iterate over L, right? Because L is like 8, 3, 10, 1, 6, 14, right? You just have to find out what the depth is. Yep. That's actually a good start right there. So the way you could do it is you could iterate over every single one of these things and check the depth at each point. So what's the depth of 8? It's 0. So we print it on the line. What's the depth of 3, 10? Well, it's 1. So we start a new line and put 3 and 10 there. What's the depth of 1, 6, 14? The depth is 2. So we start a new line and put them there, and so on and so forth. So hint, you can use the max depth function to determine what vertical level to print each node on. All right, does anybody have any other questions, like specifically about the logic or recursion or anything like that? I'm actually not sure if any of this stuff is going to be on your exam or not, because to my knowledge, none of this stuff is on the assignment 6. And Professor Moore has not written the exam yet, or at least it's not done. So I guess we'll see if it's on the exam. I don't think there's going to be too much of it on the exam, to be completely honest, because from what you've seen, like Mr. Moore is usually a pretty like practical guy when it comes to test questions. But yeah, it would be good to just have this as a reference and to understand the general fundamentals and rules of how to build a BSD and how they work. That's all the content for tonight. If anybody has any questions, feel free to ask them right now. So I'll stick around for a couple minutes, but yeah, that's all the content, guys. So if you have no questions, I'll see you on the next tutorial on Monday. You are welcome, guys. Thank you for coming. I'm really happy that Professor Moore has taken some leniency with the whole test case situation for your test 2. And yeah, I think that's really good because hopefully the average will go up substantially now. All right, looks like none of you guys have questions about this stuff. So we'll go on Avenue and feel free to play around with it and try and take on this little challenge right here. Thanks for coming, guys, and I will see you on Monday.